Where I come from, the situation is happen quite often. You have a walk in the countryside, you want to find your nice favorite picnic spot, and then when you arrive there, what a disappointment, it's a dump, because of all the plastic rubbish. Let's be honest, it's mainly people's fault, but at the same time you may have wondered, why are no scientists doing anything to improve this? Plastics, they've been around for a long time now, and despite their environmental problem, they've increased dramatically our economy and our quality of life. They're nowadays everywhere. They're in your car, not in my car. They're in your laptop, they're in the tubings you've got in your house, they're in all the packaging from your favorite soda to your favorite DVDs. They're even in your clothes, actually. Credit cards are even made from plastic, which is a nice symbol, I think, to say that the industry of plastic is an industry in constant growth that generates millions of tons of materials and weighs hundreds of billions of pounds. So why those materials are used widely? It's because they're light but robust materials. From a structural point of view, a plastic for a chemist is one or a blend of big long chain molecules that are called polymers. Polymers are long chain molecules made from a sequence of building blocks that we call monomers. The sequence can be really simple and involve only one monomer, but it can also involve 2 or 3 or even more complicated sequence, like this complicated branch thing. One of the main problems of polymers nowadays is that they're made from chemicals from oil, and although it gives a really strong and stable plastic, it's often non-biodegradable and non-easily degradable. There are some degradable polymers out there, and you may have heard of, for example, polylactic acid, which can be degraded using microorganisms or under mild thermal conditions. But usually the property of this material doesn't match the application we need. So that's what my research is all about, really. It's about synthesizing new monomers and new polymers from a renewable feedstock without the use of chemicals derived from oil, in order to have a polymer with the right properties and with a better chance to have degradability properties. The idea is simple. It's when you look at those common plastics that are used for packaging, like polycarbonate on the top or PET in the back, it doesn't take a chemist to figure out that this motif in red is in fact CO2, our best enemy. The same CO2 we want to get rid of because of the climate change, the same CO2 that reached a level in the atmosphere of 400 ppm a couple of months ago. But why are chemists not doing anything else, anything good with CO2? It's because to transform CO2, we need a lot of energy. People are trying, for example, to make fuels out of CO2, to transform into methanol. This takes a lot. Our target, to make polycarbonate, is much more accessible because we're not really modifying the structure of CO2. Our strategy, the first strategy, is to take CO2 and to couple it with another molecule to make a cyclic monomer, a cyclic building block that then can be ring open and lead to a polymer using something called ring opening polymerization, which is a technique well documented in the world of polymerization. The second approach is a more direct one, where we devise a catalyst that will couple directly CO2 with another molecule in an alternating fashion. The type of molecule we're looking at to couple CO2 with is, for example, the glycerol. Glycerol is a really interesting molecule because it's available in big quantities to us, and it's a waste of industry like the biodiesel industry or the soap industry. And using catalysis, using chemistry, we can couple CO2 and glycerol, for example, and make it this new monomer. And then open it to give a long chain polymer. And this is interesting because of an extra alcohol side, we can then tune the monomer and the properties of the material. Regarding the direct copolymerization of CO2, the main challenge is to devise a catalyst that will couple CO2 and the cyclic ethers in an alternative fashion. The other problem is that those molecules, cyclic ethers, are not really available, but however, they're one step away using an oxidation or cyclidation step from big, huge, natural, sustainable feedstock like terpene or sugars, for example, opening the door to a lot of properties and a lot of application. I am an experimental chemist, but to design the catalyst, we also get some help from quantum chemistry simulation. Those simulations help us to identify the difficult step of the reaction and then tune the catalyst. This is where we are now. We're making really nice powders, which are, I agree, a lot really far away from a consumable plastic, but we're working really hard towards new catalysts, new monomers for improved material properties in order to achieve widespread application and to have a real impact. Thank you very much.